If you are watching this video, then that means that you are ready to upskill as a Solidity developer in 2024. Now, why would you want to be a Solidity developer? Especially this year, Solidity jobs are the highest paying roles in the Web3 or blockchain industry and pay anywhere from 80,000 a year to $250,000 a year, depending on your experience. This video will give you the confidence to go from zero knowledge to 100% proof that you are a Solidity developer. And no, I do not apologize for that awful pun, because I can't wait to show you just how great this university is and how literally by learning these fundamentals, you will be able to tackle much more complicated Solidity problems and land yourself that dream role that you so desperately want in Web3. My name is Hakeem, and my mission is to help you land your dream role in Web3. First, I want to emphasize why you must learn Solidity, especially in 2024. As I said, Solidity accounts for the majority of the highest paying roles in Web3. However, in 2024, we will be experiencing the Bitcoin halvening event, which has been famous for causing bull markets every single time that they occur. Now, hashtag not financial advice, but now would be the best time to upskill yourself so when the bull market comes, you have no shortage of work and everyone is going to need a Solidity developer at some point this year. Why? Because the majority of blockchains that exist are EVM or Ethereum virtual machine compatible blockchains. So any smart contract you write for Ethereum, for example, will work just as well on Phantom, on Avalanche, on Polygon, on Optimism. These are all EVM chains and they have their own communities, their own developers, and they still need Solidity developers because Solidity developers are in extremely high demand and always have been, and that demand is exponentially increasing over time, especially as we have more adoption of blockchain technology. So, to get started, head on over to alchemy.com/university and then click on Start Learning. I'm going to sign in with my Google account. If you have not made an Alchemy account, it takes 2 seconds. And now it's going to ask you some questions. I'm going to say learn Solidity because this is the one that we are doing. However, there is also a developer bootcamp, which is an older course and a slightly more advanced course. But in this video, we will break down the brand new Learn Solidity course, which I can't wait to show you. Click next. I'm a software engineer. Do you work full time? Yes. How many years? I have 1 to 4 years. Once you have entered your credentials, you'll see the screen here, which will have the different courses available to you. These are all free courses, and the one we will focus on is this Learn Solidity, which is a brand new course. So it does say intermediate level, but I would say that if you have any experience at all with any programming language, you can complete this course. And it says 2 weeks, but we're going to do this in a couple hours. So, the prerequisites are basic coding. This could be JavaScript, Java, Python, pretty much any language that is not Solidity will help you out significantly, and that's all you technically need to know. But if you have zero coding experience, I still believe that you can complete this course and become a qualified developer just by having the correct mindset coming in. If you're brand new, you will see a lot of stuff that will overwhelm you at first. This is normal. Do not worry. You will be overwhelmed and things won't make sense. But that is the growing pains, and I'm going to walk you through each practice question and explain why I came to that conclusion. This course does have its own mentor or guide, which is this guy here, Dan Nolan, and he breaks down the higher level overview of each section and does some other coding on the side to help explain concepts. If you're brand new, I really encourage you to go through this course by yourself first and then come to my solutions to see how closely aligned we are. And maybe if you're stuck, then come to me to try and find an answer. Um, but I do suggest that you do the course first, regardless, and then only come to me when you either A, need clarification on a problem, or B, you want to see how closely your answers are with my own. So let's head over to our first one, practice data types. And we see here a basic overview as to what it is. So we'll learn basic Solidity data types. We'll use state variables to store them in the contract's persistent data storage. So now you might not know what the hell this means. If you are confused, again, I encourage you to go back to these videos and make some notes so you at least have some preliminary knowledge before you come on to tackle these practice questions. It does mention on this page that it's important to do things efficiently since all storage and computation on the blockchain will cost money. This is what makes Solidity so valued and so powerful, is that everything you write is tied to money. So whenever you're writing a line of code, just think of someone's money is going through this or has a potential to go through this, and their literal wealth is affected by the code that you write. So we have to make sure that we write safe, secure, and efficient code in Solidity. So let's begin. Start coding. The first part of this course will focus on basic data types used in Solidity. Now, to the left, you'll see a task, which is what we'll be tackling each time. And sometimes we'll see this details tab here, which will give more details as to why this section is significant. To the right, you'll see the IDE or Integrated Development Environment. It's an interface for us to type our code into, which will be compiled into bytecode using the Solidity compiler of version 0.8.2. Now, you do not need to worry about any of this as it's pre-configured for you. And you may also notice this license identifier here. Do not worry about this, it is just a Solidity standard that we use to show that this is an open source contract. Next to this, you'll notice another tab called contract.t.sol. This is the test file that gets executed for each practice question. So whenever you click test output here, run tests, it's going to run your code in here against the test file here. And as you can see, it's failed, so we don't pass this first one just yet. This is using something called Forge Standard Testing Library, which is a Foundry feature. So this entire IDE is actually using Foundry behind the scenes. If you have no idea what I just said, then please refer to my previous video on what is Foundry and some of the best practices that you will need to know. However, for this tutorial, you will need no experience with Foundry. It just helps to know what's happening behind the scenes. So let's clear this message. And one more thing I want to mention is you'll see this compile tab down here. Now, every time you write code, it will be compiled into bytecode, and any errors that you write at compile time will be caught in here. So if I just type something in like this, the compiler will say, what the hell is this on line 6? Well, really line 5. And that's because this is invalid Solidity code. Basically, this is great for catching errors as you are writing your code. And the validations tab I'll get to in just a moment. Let's start with the first task. So if we scroll down to our left here, you'll see this task down here, which is the actual instructions that you need to follow. Everything else is just information to help you understand the concept. Create two public Boolean variables, A and B. So I will say bool public A and bool public B. The next step says store true in A and false in B. Equals true equals false. Simple. Now, to run this code against the unit tests, you can either click down here or right here, or you press Command Enter if you're on Mac. So Command Enter, perfect. Now, one more thing I want to show you is in the Details tab, you'll see this ABI validation section here. The ABI is crucial for other entities to interact with your smart contract. So in the validations tab right here, you'll notice validations are passing. The way it's doing this is it's checking your contract's ABI or application binary interface here, and then it's comparing it to what it's expecting in the backend. Now you cannot see what they are checking for obvious reasons, otherwise you could just cheat. In this example here, we have a contract that has one Boolean variable, and this is the ABI for the overall contract. It has an input, a name, and some outputs here that are tied to this variable. So the variable is called my variable, and the type is Boolean. This state mutability is view, and the type is a function because all public variables have an innate getter function. So that's why it says type function here for the variable. And this ABI is what a front end or a back end server would interact with to call your smart contract. So for this tutorial, you do not need to worry too much about that. However, it's good to know that an ABI is essential for applications to interact with your smart contract. So let's move on. Unsigned integers. So an unsigned integer is basically any number in Solidity that cannot go below 0. Now there is a max number, but you do not need to worry about that in this tutorial. Let's scroll down to the task at hand. It says let's create 3 public storage variables in our contract, a, b, and sum. So define a as a uint 8 with an initial value between 0 and 255. Let's do that. Uint public, uint 8, public a will be 5. And then another one called uint 16, public of at least 256, which will do 257. And then the other one, sum, should be a summation of those values. So uint 256, public, sum should be a plus b, so it equals a plus b. Now press Command Enter. There we go. Before we head over to the next stage, click on Details, and it mentions integer overflow and underflow. Now this used to be a very big deal, as it mentions in previous versions of Solidity. You would have to be aware of something called overflow and underflow, which is when your numbers go outside of the minimal and maximum limit for that given data type. So for uint 8, the range here is between 0 and 255. So if your value went below 0 or above 255, you would get an overflow or an underflow, which would then either reset your variable to 0, or it would get set to the maximum number, which is 255 for a uint 8. Now the maximum number for 16 is different compared to 256. If you're curious, I'll whack them up on screen now. Okay, let's head over to the next section. Signed integers are rarely used in Solidity because we don't really want negative values when dealing with money. So it's basically the same thing as a uint in terms of the data type. So you'll have a uint, you'll have an int 8, int 16, int 32, so on and so forth. As you can see here, the range of uint goes from 0 to 255 for uint 8, but for int 8 it goes from -128 to 127. They both cover 256 values though, which is the maximum number of values that you can express with 8 bits. The task is to create 3 public storage integers a, b, and difference. Declare the variables a, b as int 8. One of the values was positive, the other must be negative. Okay, so let's have int 8 a equals 5. Oops, let's make it public. And then int 8 public b equals -5. Declare the difference as an int 16. So int 16 public difference. And the absolute difference is found by subtracting a from b. So that means a minus b. That would be 5 minus -5, which is 5 plus 5. So we should get 10 here. Perfect. So let's head on to the next stage. So far, we've seen booleans, which is a true or false value. Then we saw uint and int, which is an unsigned, which is a non-negative number, or a allowed to be negative number as an int. Now we're seeing string literals, which is as we can see here, a defined string. A string in Solidity can be declared as a type byte or a type string. You generally use a string type when you're not sure how long the string's going to be. But if you know the string's going to be tiny, like hello world, then you would use something like bytes. Create a public bytes 32 storage variable. So bytes 32 public message1, which stores a string literal of hello world. Now you can use single quotes or double quotes, up to you. And the next one is a public string, so string public message2, which will be a string literal that requires over 32 bytes. To get a string that is over 32 bytes, so scroll up here, and in this example, they actually give you one. So the maximum value, let's say this top value here, copy and paste it in, and this is the maximum value. So if we do one more C, this will now be longer than 32 bytes, and it should pass the test. So let's press Command Enter. Oh, we forgot our semicolon. Now let's run the tests. So this string literal here needs to be quite literally hello world. And in fact, we will use double quotes from now on because it does change it changes the color of the string. So let's just Command Enter this. Next stage. Enums are fantastic for writing cleaner code, especially when you have different variations of something. So in this example, we have a foods enum that can represent apple, pizza, bagel, banana, so on and so forth. And let's head over to the task. If the enum provided, in the enum provided, you'll see there are 4 types of foods. Take the values and store them in food 1, 2, 3, and 4. Okay, so simple. The syntax is foods.apple, foods.pizza, and we'll say all of them. Now you can put anything in here, to be honest with you. You can even change it. Perfect. Next stage. That completes the first subsection of the course. So if you click on number 1 over here and back on smart contracts, you'll see that this is now complete. We can close this, and now we're on functions and value types. So let's click on practice Solidity functions. We've learned how to store values. Now it's time to learn how to modify those values by using functions. Functions are essential in Solidity. Functions allow us to execute custom logic within our smart contracts, be it sending ether, receiving ether. Now, ether is just another name for the native currency of Ethereum, so this changes based on whatever blockchain that you're on. I mentioned earlier that public variables have an innate getter function, so you can call them. And in this example, we're using that innate getter function by just declaring x again. And inside of this change x function, we are reassigning it to the value of 5 from 3. So this is how you update state variables or storage variables in Solidity. Task 1 of Solidity functions. Constructors are executed on deployment of the smart contract, and they are only executed one time. Let's scroll down to the task at hand. Create a constructor which will take a uint as an argument. Okay, so constructor takes a uint, and we can call it whatever we want. The example says to take this uint and store it in a variable called x. So I'm going to call this x as well, and we're going to say x equals x, uint public x. So now, if you head over to our details tab, it mentions something called variable shadowing. Because we have given it the same name, Solidity will catch that and warn us about this. Click on your compiler here, and it will say this declaration shadows an existing declaration. So this is a warning to let you know that this will cause problems. Easy fix for this is to give an underscore to constructor parameters so that they are not the same variable name. Underscore x is different from x. Let's run the test, Command Enter. In the second task, we'll be exposed to external functions for the first time. These are functions that are called by an EOA or externally owned account, which is a fancy term for a cryptocurrency wallet. In our case, we'll just say MetaMask. So let's create a function here. So create an external function, increment, and then parentheses, external, curly braces, that will add 1 to the state variable x. So it'll be x plus equals 1. This is a syntax used to say x equals x plus 1. We can shorten this or concatenate this into this syntax here, so it's just cleaner, and most developers or all developers can understand this. Okay, so let's press Command Enter. Perfect. Next stage. Now we're going to learn how to return values from functions. So below this, I'm going to say, let's scroll down, create an external view function add, which takes a uint and returns a sum. So function add, it takes a uint parameter, let's call it a, external view. View just means that this function does not interact with any state, so it does not touch the state variable at all. Real quick, I do not need to add in 256 here because it's assumed that without that, it's using uint256 under the hood anyway. But if you want to be specific, you can say uint256, but it's just cleaner again just to say uint, as the compiler already knows what you mean, which is the uint256 data type. Okay, so now we need to add these two together. So it's going to return a plus x. Simple. Perfect. Next stage. In the fourth challenge, you're being introduced to the concept of console logging using Forge standard library, which is a Foundry feature, as I mentioned earlier. So all you have to do is console.log secret message, and let's run this. It's going to fail the test because we haven't actually returned anything. Now the console log is saying return the value 794 to win. This came from the Calldata secret message, which means that it was passed in from an external call to this function. Don't worry about what that means. We'll elaborate on this, I believe, in the next section or the one after that. So now we've console logged the value, we know what it is. Just simply below this, return 794, run it again, next stage. Pure functions do not read or write from state. So in the previous one, you saw it read from state, but this one does not. So let's scroll down to the task, create an external function. There's a function called double. It's going to be external pure, and it's going to return a uint value. Oh, it's going to take a uint parameter as well. Let's call it a. Let's say return a times 2. So this is the syntax for multiplication in Solidity and most programming languages. Function overloading is a feature that is available in most programming languages as well. In this example, we have a function called add, which has 2 parameters, and below that another function with the same name, but it takes in 3 parameters. Each function have their own logic in them. So the reason why we can do this is because this will generate one function signature, and this second one will generate a different function signature, so they do not overlap when you try to call them. Let's scroll down to the task, create another pure function called double, which takes 2 uint parameters. So function double uint a and uint b. Double both of the arguments and return both of them in the same order that were passed into the function. So we actually need to use something called tuples here. So I need to change this to uint, uint. And then in here we say return a times 2 and b times 2. This is a syntax to return multiple values in Solidity. Command enter. Whoops, I forgot to label this external. Now let's run it. Perfect. Congratulations, you have now completed the first part of the Solidity course. Now you have the basic understandings of data types and functions. Let's move on to something more advanced, which is message calls. This section will focus on message calls, which is how we actually communicate with smart contracts. And so this involves smart contract to smart contract communication, but also your private key or your wallet, your crypto wallet, to the smart contract. I mentioned earlier something called externally owned accounts, which is mentioned here. Now, this is just a concept, and in Solidity or Ethereum, this is just a this just means your private key or your wallet, your crypto wallet, your MetaMask, your Coinbase wallet, so on and so forth. And technically speaking, it's actually no different from a regular smart contract, which is referred to as a contract account. It's just that it's easier to think of them as two separate entities since one requires a user's private key to sign data, whereas the other one doesn't. So let's begin. Start coding. The first task of sending Ether is to create a public address. So let's call it address public owner. Now let's create our constructor, which won't take any arguments. And instead, we're going to use something called message.sender. So we're going to say owner is equal to message.sender. This is part of the call data that is passed to the smart contract from the user or the deployer, which contains information such as the current sender address, which would be, let's say, your address if you're the one deploying it, and we're assigning it to the state variable called owner. And from this, you can have functions that can only be accessed from the owner of the smart contract. Let's press Command Enter. Perfect. Next stage. Receive Ether. The task this time is to add a function to the contract that will allow it to receive Ether on a transaction without any call data. So in this example here, it mentions a receive function. So let's do receive external payable, which is simply going to accept Ether coming in. So if we press Command Enter, that passes. Real quick, I want to show you the unit test for this. So in Foundry, you can run these tests in a particular way. So you'll notice something called hoax here, which means that we are pre-funding this address with some Ether, which is the native currency used to send value or send money across the network. And then they're simply just getting the address of the contract that's just been deployed, and then they're calling it and passing 2 Ether to it from that address message sender. Okay, so let's move on to the next section. Tip owner. Scroll down to the task. Let's create a way to tip the contract owner. Create a public paper function tip, which sends any of its received Ether to the owner. So, function tip, which would be a public payable. If this is too fast for you, I encourage you to go through the course by yourself first and properly read through these sections and watch the videos provided by Dan Nolan, the course mentor. So let's scroll down. Just to recap, receive is an innate function on smart contracts that allows them to receive the native currency Ether. And you could even do some additional logic inside of this. And payable means that the function can actually receive Ether. Without this, it would error out. We have just made a tip function that's public and payable, and we need to send all of the Ether to the owner, which is defined up here. So let's do bool success, comma, equals owner dot call, curly braces. It's going to be value message.value, because remember this is part of the call data being sent to this function, And then we say close parentheses, require success. So this require statement is saying if this is not true, then revert the transaction, and require will not consume any gas. And you'll learn more about this in a future section. Perfect. So the next section is charity. Now we're going to use this keyword, which is a special reserved word, and you may have seen it in previous languages. It accesses the current class, and if you're familiar with something like Java or TypeScript, this will access the current class's properties, and it is the same thing. So you can, and in Solidity, it's basically the same thing. So you can think of a contract as a class, and so we're going to access the contract's address by doing typecast to address and going this dot or typecast into address. So you typecast to address and you just access this, which returns the address of the current contract. A similar syntax is used to get the balance, which is again in Ether. So you can do address this dot balance, which is what we'll do right now. In the constructor, add in a new parameter. Let's call it charity. In fact, underscore charity. And then we'll make a state variable called charity. We will assign it to what was passed in the constructor. And in this tip function here, we're not going to bother. So below the tip function, we say donate, which will again be public and payable. The code will look similar to before, so bool success. We don't care about the second parameter there. And we're going to say charity.all value, and we will use the syntax we just saw, so address, typecast to type address, and get the balance, parentheses, and below that we say require success. If you notice, the validations is half green, so let's see what it says. Expecting donate to be non-payable, not payable. Okay, so we don't need this to be payable. Great. The reason for that is because we already have a receive function here which receives ether, and when this one gets called, it's actually going to take everything from the contract itself, hence this syntax here, and then donate it to the charity. I understand the syntax can be slightly confusing, but think of, we are calling the charity, we're calling their name, and then we're giving them all of the currency on this contract address. So let's move on. Self-destruct is a very controversial way of cleaning up smart contracts on the blockchain. Self-destruct not only wipes away the smart contract entirely, but it will also refund any ether that's left on the smart contract. To the left, you'll see that in the self-destruct function call, you can pass through an argument to receive the ether. So, you could say, whenever the smart contract is destroyed, send all the money to me and no one else gets it, which again sounds kind of dangerous, but there is a good reason why this opcode exists, and I'll dive into that in just a moment. So the goal, when the donate function is called, trigger a self-destruct in the contract. It will send all the remaining funds to the address passed in. Okay, so in this donate, below this, we can say self-destruct. Again, this is an innate function, part of the Solidity. So self-destruct, and we pass in payable charity. The compiler will then complain, saying that self-destruct has been deprecated, and eventually will eventually undergo breaking changes. So it's recommended not to use it for future versions of Solidity that are coming. Let's click X, run this test. Perfect. Real quick, in the details, The only reason the only reason to use self-destruct is for upgradable smart contracts. This is an advanced concept which we do not go into in this course, but essentially if you have an old smart contract on the blockchain that you no longer want to refer to, and you want to deploy a new one, you can destroy the old smart contract to only point to the new one. And this is good, especially if you don't want people to use the old code because there might be bugs or other problems in there, maybe inefficient gas, problems in there that you don't want to bring to the new contract, so you just blow it up entirely. In Solidity, the revert keyword does exactly what it says. It reverts a transaction. So there's three kinds of ways that we can revert something. If you trigger any one of these three keywords here, it will actually roll back any changes that were made to the blockchain. So let's begin. Constructor revert. In the first task, we've been asked to implement the revert keyword within the constructor. So add a payable constructor method that requires a 1 ether deposit. If at least 1 ether is not sent to the constructor, then revert the transaction. This means you cannot deploy the contract without sending it at least 1 ether. So let's do construct. So let's do constructor and then payable. Inside the constructor, you want to define a require statement, which we can pass through some sort of condition. So we want to say message dot value, so that's the call data that's being sent during deployment, must contain a value of 1 ether, comma, and then we can add a string literal to give an error message that can be read from the front end or back end. This error message can be whatever we want. So let's say at least 1 ETH required, semicolon. Perfect. Now, if we look back at the task, you'll notice that you can actually use custom error messages in Solidity. These are not only more efficient with gas, but you can customize the error message and pass through arguments to the error. There's two ways we could have approached this. One is using the require syntax here, or we could have done this and said if message.value does not equal 1 ether, and then inside of this if statement, we can say revert at least 1 ETH required. And if we run this test, again, it passes the condition. In the details tab, you'll notice the assert keyword is mentioned in here. Now there is a key difference between require and assert. So require and revert are the same thing. Require is just syntactic sugar instead of using if and revert as you just saw, whereas assert is a completely different keyword. Assert is used to make sure that a piece of logic is always constant, or you might hear the word invariant used in Solidity. So in this example, where we have a function that withdraws everything, it's sending all the balance of the contract address to a given recipient, and then below this, we're asserting to say that the balance of this contract address should be 0. And if it's anything but 0, then something has gone terribly wrong somewhere. And the difference is that this is making sure that something should never happen, whereas the require statement is just checking to see whether or not a given parameter is true or false. The require keyword refunds gas to the message.sender and revert all changes made during that call, whereas the assert keyword does not refund any gas and it still reverts the transaction. So it's more like a punishment. So you can think of assert as a punishment of sorts for executing this piece of code that should never be triggered. Okay, so let's move on. Restricting by address. So in this one, it's saying we can provide certain roles to an address. So the goal of this task is to create a public function called withdraw that can withdraw all the funds from the contract, but only a certain account or address can call this function. So let's create a public function, withdraw public, and we're going to send them to the deployer. So we need to do the same thing as before, which will be address owner, and the owner will be equal to message.sender. So on deployment, we're assigning a contact address. Make sure this is public. Require that only the and then within this withdraw function, we're going to say full success. This is the same syntax we saw in the previous section. If you're not sure, head back to that. And we're going to call the owner, pass through a value field in here, and it's going to be all the funds with the contract address. So address this dot balance, and then we're going to require success. At the moment, anyone can call this withdraw method, so we need to add a require check to say only the owner can do this. So at the start, require message.sender is equal to owner. Then we'll say only owner can withdraw. Great, let's move on to the next section. Owner modifier. The owner should only be able to call certain methods on the contract, and this is a common pattern that you'll see in Solidity smart contracts. And in fact, there is an Open Zeppelin library called only owner, which implements a modifier, which you're going to see right now, to only allow the owner of a contract to trigger certain functionality. So in this example here, the goal is to update the only owner modifier to require that only the owner address can call these without reverting. This is the first time that you will see a modifier, so the syntax is different to a regular function. So down here you'll notice a modifier keyword. There is no visibility keyword like public. There is no modifier like pure view or anything like that. It's just an internal function that gets called before any of these functions can execute. So we only want to require the owner to access this. So we want to say the logic is the same as what we just did in the previous set. The logic is the same as before. So require message.sender equals, and we say only owner. And then this underscore semicolon, this underscore triggers the execution of the function where it's being used. So the way you apply this is here, the only owner modifier has been applied to each function in here. Modifier checks to see if the owner is calling the function, and then when it hits this point here, it will then execute the logic within the function. Perfect. Next stage. Calldata is what we use to communicate to smart contracts and also how smart contracts communicate with each other. So an EOA or externally owned account, that is a cryptocurrency wallet, the format looks like this. So let's say you want to call a method approve on a contract that takes a uint. We can target this function by taking a signature and hashing it with a Keccak256. Keccak256 is a commonly used hashing algorithm used in Solidity, and we'll see this in just a moment. So the Calldata contains a signature of this function. So remember, signatures exist in most programming languages, and it's how you identify any specific function. It takes those first 4 bytes and it will then combine it with whatever parameters are in that function. In this example, we'll have a uint, right? A uint 256. So it will hash that value in a bytes 32 format or 256 bits, and that hash will represent the given function that we are trying to target. So let's begin. Start coding. Interfaces. The easiest way to enable one contract to interact with another is by defining the target contract. Interfaces serve this purpose. So if you've come from a different language before, such as TypeScript, in TypeScript, interfaces are used a lot to understand what a given type contains. In Solidity, an interface just tells you what functions a smart contract contains without actually containing the functionality. So here we have an interface called Hero, and we know, sorry, iHero, and we know that the iHero interface implements a function called alert. So if we look at the hero.sol here, it does indeed include the alert function, but it doesn't include the actual functionality. The goal of this task is to use the iHero interface and the hero address passed into it to trigger the send alert method. So in here, inside of this function, we can typecast the parameter, which is of type address, to the interface iHero. So we say iHero pass through hero, which is of type address, and now we can access the alert function on the interface. So we say dot alert. Perfect. Signature. In this context, we're referring to the function signature, but in Solidity, you may have heard something called signing a transaction, which requires a user signature. That's a completely different concept and not taught in this course. But a function signature is a much more simpler idea. And in this example, all we have to do is fill in the function signature for the hero's alert function and pass through that signature in its 4 bytes format. In the previous example, we simply called the alert function by using the interface, but this is a lower level way of interacting with different contracts. So inside of this catchat 256, all we have to do is pass through alert. Now notice that this requires quite a few steps. So we are first getting the bytes for signature by hashing the actual name of the function here as a bytes4 format, and then we're doing hero.call passing through an ABI.encode packed method that contains this signature here. Quite a lot to do. So is there a simpler way we can do this? Well, yes. In the next section, we have with signature. Now in here, we're using the ABI.encode with signature method, which handles the hashing for us. So in here, I'm going to say ABI encode with signature. Then we pass through the same syntax before, so it'd be alert. But this time, the alert function has been updated, so it contains a uint and a bool, so 2 parameters. How do we pass this in? As shown on the left here, you must define the full syntax for the uint. So it's uint256, and then the other one is a bool. This cannot have any spaces in, otherwise this will error. And then after this speed, and then after the string literal, the parameters this time are the number of enemies. So you just pass through enemies and then armed, which is the parameters. So you're passing through these parameters. All we're doing is passing in these parameters from the function into this API encode with signature method. Great. Next section, arbitrary alert. If we take call data as an argument, we can pass that call data along to another contract. So now we need to be able to relay information between contracts using call data. The sidekick needs to be able to relay any call data along to the hero, update the relay function to take the data and send it to the hero as call data. Similar to before, we do the syntax of bool success, and we're going to call the hero address. We do not need to typecast it this time because we're not actually calling a specific method, we're doing a low level call to this address. This time we pass through the data into the parentheses and not the curly braces. So you can just do parentheses and say data. Require success. Great. So this time, just to clarify, we do not need to define a value field. We're just passing data directly to this address. Fallback. If any of the function signatures that you're trying to call do not exist on a contract, there exists a default method called fallback that gets executed. This includes any potential errors you've made in the function signature. So maybe if you did a typo in that string that we saw earlier, it would trigger a fallback. So we can just call anything here. So I'm going to just say bool success hero.call. Then I'm going to pass through some random stuff, random, acquire, don't need this second part. Now this fallback function you can define as anything you want, but typically it just bounces back and reverts a transaction. Escrow.sol. This is a commonly used contract to understand how different addresses can interact with different functionality within a given contract. So, an escrow is just an agreement often used when transferring funds in exchange of a good or service. So, think of like you hire somebody, a contractor, to do some work for you, and that money is held in an escrow account. So, in this example here, we have a depositor, which typically would be uh, a depositor, which would be the client, deposits their money into a contract called escrow.sol, and the beneficiary is the contractor doing the work for the client. And typically, there is a third party called an arbiter that gets to approve the transfer and handle any disputes between the client and the contractor. But the beauty of Web3 is that we can remove this arbiter entirely and just have a smart contract that dictates this. But in this example, we do have a third party that does get in the way of the disputes. There are many use cases for escrow accounts across real estate, charities, marketplaces. It's easy to write and also powerful. Part 1, Setup. So the first stage is let's create these addresses as public. So simple address, public, depositor, address, public, beneficiary, and address, public, arbiter. Oh, I typoed here. Let me just copy paste this in. Now run it again. Next stage, constructor. Each time that a depositor, arbiter, and beneficiary come to an agreement, they can deploy a contract. They will ask the arbiter and beneficiary for addresses that these two parties have access to. Then the depositor will provide these addresses as arguments. Okay, so basically, we need to define who these addresses are, which gets decided during the deployment of the contract. So let's first create a constructor. Takes in two arguments, an address for the arbiter, underscore arbiter, and an address for the beneficiary. Spelled it last time. The depositor is the one making the agreement. So we say depositor equals message.sender. And now we can just assign these storage variables to the ones passed through in this constructor. So we say arbiter equals underscore arbiter, and then beneficiary equals underscore beneficiary. Next stage, funding. Now it's time to fund the contract. The depositor will send some ether to the contract, which will be used to pay the beneficiary after the transfer. So now we need to make this payable. So payable. That's the only step for this one. After the contract has been deployed, with the appropriate amount of funds, the beneficiary will provide the good or service. They are now secure in knowing the money is on its way. Once the good or service is provided, the arbiter needs a way to approve the transfer. Let's add this mechanism to our contract. So we need an external function here called approve. And this will move the funds in the contract to the beneficiary's address. So we say same. So it's the same syntax as before. Bool success, comma equals uh, beneficiary dot call, and the value will be all. And the value be everything on this address. And there's no Calldata bytes being passed through, and we require success. Otherwise, the transaction will revert. Approved. Now we need to lock it down so only the arbiter can call this. So if anyone tries to call approve, revert the transaction. Let's add a require. So this time I would use now I could just add in a require statement here, but best practice is to have a modifier. I could Now, I could just add in a require statement at the beginning, or we could use a modifier as we saw in the previous section. So let's do that one. Below this, modifier, only arbiter. And in here, we'll say require message.sender is equal to arbiter. Otherwise, we scream at them and say only arbiter. And then we execute the function. Now we just add this on to the end of this and say only arbiter. Perfect. Events. Without events, we would have no idea what is happening on the blockchain. There are so many transactions per second that we just could not keep up with it. But luckily, events allow us to index data so that we can fetch it at any given time in the future. And this is critical for both front end and back end servers to listen to the blockchain so they can react to these changes. Now, in this example, it says the same thing as what I just said, that front ends can listen to important blockchain events and show the most up to date information to their users. An event can be declared and emitted like this. So you define it like this and you emit it within the function call. Events inform us of changes happening to state on the blockchain. So why not just update state? Well, because events are very cheap compared to updating a state variable. That's why. So below this, we'll have an event called approved, which will accept this will accept a uint. Then within the approve function, we emit approved and pass in the new balance of the beneficiary. So we can say beneficiary dot balance. Great. Solidity arrays. Arrays are not used that much in Solidity because it costs so much gas to loop through a big array. And the preferred data type is something called mapping, which is in the next section. But for now, we still do use arrays for certain use cases when the data is in a structured sequential format. So something like token IDs, for example. So let's start coding. Fixed arrays. So fixed size arrays have a set amount of values at compile time. We can declare fixed size arrays using this syntax. So we can declare the size of the array in these curly brackets here. And if you notice, we can use the array for any data type pretty much. So we have an array of uints here, which is of length 3, so 1, 2, 3. We have an address array and a Boolean array here. These arrays have their size determined at compile time, so they can't change during runtime, which is different. So in programming, you have compile time and runtime. So right now, what you're seeing is compile time, meaning if I type in some dodgy stuff here, the compiler will catch errors, whereas runtime is executed once a contract is actually on the blockchain and can't be changed. The above array declarations will work for state variables inside of a function. However, we will need to specify the data location of an array. So this is where data location is first introduced in this course. So you can see we used a memory keyword here after we define the type of array and its size. We give it the name and we give it an assignment. And then we assign the value to the variable. So the data location is memory. Memory is temporary and will only last as long as the transaction. So as soon as that transaction ends, this numbers array is completely gone. So it's not written to storage. The other data locations are Calldata for referring to message call arguments and storage for persistence. More on this in just a moment. We can retrieve elements using this syntax here. So you have the numbers variable here, which is a uint array, and you simply just say the index that you want to access. Now the index is where the elements are stored within an array. So the length here is 3 because we have 1, 2, 3 values in there, but the index starts at 0. So it's 0, 1, 2. So just think of length minus 1 as the index that you want to select for. For loops in Solidity have similar syntax as JavaScript and other C family languages. So you're saying this uint I will loop through the length of a given array. In this example, it's just hard coded as the number 10, but you'll see what that means in just a few moments. And then this I++ syntax is used to iterate on the uint I here. The goal of this task is to create a pure external function, so it's a function sum, which takes a fixed size array of 5 unsigned integers. So we say uint and then 5 memory, and we'll say R, or short for array. And does it return anything? Nope. So we're going to say external pure. In here, we find the sum of the integers and return it as a uint. So now we will have to use what I just said, the for loop, and restrict it to the length of this array. So we say for uint I equals 0. So we instantiate a temporary memory variable here, is less than r.length semicolon I++, so we iterate each time, and then curly braces. Inside of here we say, oh, we need to assign the sum, so we need to get the sum of the integers. So we need the sum of the unsigned integers within this array. Before this for loop, we can say uint total, not sum, total equals 0, and then we're going to say total plus equals, remember the syntax, so we're saying total equals total plus, and then we say r square brackets I semicolon. So we're saying total equals total plus the value at this index in the memory array. We then return total, which will, so once we've looped through, oh, we need to actually say up here, returns uint. So once we've actually looped through this array here, it would then return the total amount. Let's run the test. Great. Next stage. Dynamically sized arrays. We can also create arrays in Solidity with the sizes unknown, so we have a dynamic array. Create a pure external function, sum, so the same thing as before. So function sum. This will take a dynamic array of unsigned integers, memory, and we'll say R, external, pure, same as before, so return uint, and then in here we say total, oops, uint total equals 0, for loop, so define the variable, I equals 0, semicolon, I is less than r dot length, so we don't know how big this array is going to be. Now in Solidity, that is a red flag. You ideally want to have some sort of restriction in place, otherwise it can consume so much gas that it prevents the whole block from going through and can cause all types of congestion on the blockchain. So typically you won't see this pattern used in Solidity, but I digress. So semicolon, and then I++, curly braces, same as before. So the same thing as before, total plus equals R, I, and then outside of this we return total. Next stage. Storage arrays. Now with storage arrays, we can actually access the push method. And when we use the push method, it adjusts the length of the array. So in this example, we have an empty storage array. In this example, we have an empty storage array here, and the constructor is pushing in the value 3 at index 0, so the length is 1, 4 at index 1, so the value is 2, so on and so forth, and we're accessing the values at index 0 and 1, which is 3 and 4. The goal of this task is to create a public dynamic sized array, so we say uint public called even numbers, and then create an external function, called filter even, which takes a dynamic sized uint array again. It's going to be external, and it's going to return, and it's not, this one won't return anything, so it's just going to be external like this. So similar to before, we have a for loop, but first we define a uint called total, which would be, actually, similar to before, we have a for loop, but we don't care about counting the total amount, just the even numbers in a given array, and then pushing it into this state variable here. So we say uint I equals 0. By the way, this can be any letter you want. It could be J, K, LOL, whatever you want. I is less than R dot length, and then I plus plus. After this, we will say the way you find even numbers in any programming language is using the modulus or modulo operator, and you divide a given number by 2 to give the remainder. If that remainder is anything except for 0, then this is an odd number. However, if the modulus operation of a given number is 0, that means that that number divides into itself perfectly, therefore it is an even number. So here we'll say if r I modulo 2 is equal to 0, we then push this value into the storage array. So we say even numbers dot push r I. And so this is a, now we run the, let's run the test. Perfect. Next stage. Memory arrays do not have a push method, and that's because you define the size of the array during its initialization. Let's see what that means. So if I scroll down here, our goal is to create another pure function that filters out even numbers. Find all the even numbers and add them to a new array in memory. This array should contain only the even numbers, then return this new array. So let's just go through this again one more time. Create a pure external function called filter even, which takes a dynamic size array of unsigned integers as its only argument. Then we need to find all the even numbers in that first array passed through and add them to a new array in memory. This array should contain only the even numbers of the first array. So we need 2 loops here, and as I said before, the length of the memory array has to be predetermined. So that will be determined based on how many even numbers are in this first array. Let's begin. So let's define our function filter even, which takes a uint dynamic array called R. It'll be external, and inside of here, let's say before we continue any further, in the Details tab, it does tell you how to tackle this problem. it says you basically do need two loops. And in the first loop, you're just counting the number of elements, in this case, over 5. In our case, it would be how many even numbers are in this first array. And then, based on that count, that will be the length of the memory array we will create to then store all of those even numbers. And actually, I just realized that I don't need to have this as memory because we're not manipulating this array. We just want to have it as Calldata, as it's an external function and we're only doing read operations. So, and based on this, I'm actually going to return a uint array of type memory. So thank you, details. Our first variable I will call count. So this will count how many even numbers exist. Initialize it to 0, and then create our for loop and say uint I is equal to 0. Now we're going to loop through the array dot length and then its array I. Within here, we will say same as before. So if r I, so the value at this index, the modulus result of this, and make sure it's 0, so it's an even number. We're going to increment count to count plus equals 1, or we can just say count plus plus. Once we've got the count, we can then define our new memory array. So uint, the syntax is slightly different, and you can see it here. So it's uint memory. We're going to call this even numbers is equal to new uint and then square brackets, and then we say the length of this array. So it'll be count. Because this even numbers memory array can only contain the even numbers from the initial array, we have to be selective as to what index we are adding the even number to. We have to track the index where we are currently at in this memory array, because remember, we cannot use the push method to just add things in sequentially. We need to track what index we are at. So we say uint index or current index equals 0. Now we can loop through the first array again. So uint I equals 0. I is less than that length. Let's increment I. Then we say if r I modulus 2 equals to 0. So if we have an even number, we're going to assign the current index to that number. So the way you do this, even numbers, we say current index, then we equate it to the value of the array. Then finally, we can return even numbers here. Great, so everything looks good. Let's just close this down, run the test. Okay, there's some errors here. A equals B not satisfied. We forgot to increment the index, so that after this, so after we assign the current index's value, we need to increment the index. So we're going to go from 0. So the current index will start from 0, then go to 1, and we're gonna let's say count is 5, right? Current index will be 0. So the first time it finds the first even number, index will increment to 1, and then 2, and then 3, and then 4. So the index starts at 0, ends at 4 if the length of the array is 5. Remember that, because it's 0th index, but the length is always 1 above the 0th index. Perfect. Next stage. The Stack Club contract will have many members like a club or an organization would. We'll track these members by keeping a list of addresses. A stack is just a data structure used in programming languages that follows the first in, first out rule. So we're going to copy the same data structure and create a dynamic sized array of addresses. So This task wants us to create a dynamic sized array. So it's a uint, oh sorry, let's have addresses. So address, members, create an external function, so function add member, which has a single parameter and address, new member, external, and all we're going to do is add this to the array. So we'll say members, because remember this is a storage, because this is a storage array, we can just push it in. So members dot push. New mema. You know what? I'm going to keep that. New mema. Meant to say member. And then we create a public view function that takes an address and returns a ball indicating whether the address is a member or not. So a public view function is member, takes an address, member, public view, and then it's going to loop through this array. So it's going to say for uint I equals 0, and then increment. If you notice, even though we are engaging with the state variable, it is still a view function. That's because we're not writing to storage. If you read from storage, then this can be a view function. Now within here, I'm going to say if members I equals member, return true. Otherwise, after the loop is finished, return false to indicate that none of them contain the member that was passed through. So we have to update this to say returns for next stage, stack club 2. Storage arrays also have a pop variable or pop method. So our goal is to create a constructor which will add the deploy address as the first member, and then we need a method to remove the last member. So in our constructor here, and in here, we're going to add the deployer to the first member in this array. So we just do members.push message.sender, as that is the current caller of the deployment. Then we need to add a function down here which will remove last member. It will be external, and this will just remove the last member. So we just do members.pop. But it says here, ensure that the remove last member function can only be called by an existing member. Now we could use a modifier here, but since we've already defined an isMember function here, let's just use that instead. So in this function, we can just say require isMember, by calling this function here, pass through message.sender. Otherwise, you are not a member. The same logic can be applied to the add member. And let's just clean that up. Great, now let's run the tests. Perfect. Structs provides Solidity developers way to define custom data types. So in this example, we have one called an account, which contains a uint property called balance, which contains the account balance, and a boolean to say, is his account active? Below, we can see an example of how structs are used in a smart contract. So we have contract A, which has two state variables, one called owner of type account and one called recipient of type account. And then contract B is using something called a mapping to map an address to a specific account. We will see mappings in the next section, so for now, let's continue with structs. Vote storage. With structs, we can create custom types in Solidity that are essentially groupings of variables. So in this example, we have an enum and a struct. Now, do not get confused with enums and structs. An enum is just a way to provide what's called syntactic sugar, so it's easier for developers to understand what the code is doing. Whereas a struct is an actual custom type which has real programmatic implications, and you'll see what I mean just now. Your goal is to create a new struct called vote that contains two properties: a choices choice and an address voter. So we're using this enum as one of the properties and an address. So let's do this below. Remove this to-do line. We'll just say struct vote. It's going to have a choices choice property. And then below that, we have an address called voter. Perfect. Then create a public storage variable called vote, which is of the vote type. So now we get to declare a storage variable or state variable. The way you define the state variable is just to say vote public, and it says to call it vote lowercase. So the uppercase indicates the struct type here, and then public is the accessibility of this state variable, and then vote is the variable name itself. Finally, in the create vote function, create a new instance of vote. So now inside of this function, the way you create a new instance is just to say, we say vote equals vote. We are now creating a new instance. And so what we're doing here is we're pointing to this storage variable right here, and we're instantiating its value. So we're saying, okay, the first parameter is a choice, which we're passing through here into this argument. So we say choice. And the second one is a message.sender, which is an address. Okay, let's run this. Great. Now, one more thing I want to say, let's go back. In the details section, you'll see there's two different ways we can initialize a struct. State which property we're actually assigning to. If this was a big contract, you would have to scroll all the way up, look at the struct and see, okay, what parameters, what properties does it contain? So this syntax here is more verbose than what we just saw. That means there's more code, but it does make it slightly more readable, which can be useful if the struct is really big and you got like 10 different properties on here. Vote memory. When you're returning structs or other reference types like arrays, you have to clarify where the data is coming from using location keywords, storage, memory, or Calldata. However, for external and public methods, you cannot use a storage keyword for the return parameter. The storage keyword will provide a direct reference to the location within the contract's own persistent storage, which cannot be accessed outside of the contract. Use memory or Calldata instead to return a copy of the data. So this is where we first get introduced to the concept of data locations. And in the next section, I believe, there is a whole section that defines these three keywords in detail, which I'll dive into. So let's scroll down to the task. Create an external view function called createVote, which takes choices value as a parameter and returns an instance of type vote. Create vote. It takes a choices parameter and its view. As it said, we can only return a memory type, not a storage. So we're going to return memory, a vote struct here. So a vote memory struct. This function should use a choices value as a message.sender as the values to create the vote. If you notice in this question, there is no state variable called vote anymore. So we can just say vote vote or vote memory vote equals vote. And then we're going to do choice and message.sender. And then we simply just return vote. We can do this because we don't have that state variable anymore called vote. Let's run this. Perfect. Next stage. Struct arrays. We can create an array of struct types just like we would with any other data type. So we can have an array of accounts here, which is pretty cool. And in our case, we're going to have an array of votes. So create a public storage array of the vote struct called votes. So public storage array of the vote struct. So we say vote, and then the square brackets, and then we say public votes. In the create vote function, use a choice parameter and the message.sender to create a new vote and push it into the array of votes. Vote memory new vote equals vote choice message.sender, and then we can push this into this state variable here, which contains the array of structs. So we say votes dot push new vote, and this does not return anything, so we don't have a return keyword here like we did in the last one. So we instantiate a memory vote struct, and then we push that into the array of votes. Choice lookup. Accessing struct properties. It's time to access some of the struct properties we've stored. You can do this using the dot operator. So we can say, in this example, we have a struct called human that has a name and age. To access any of the properties, you just do human.name or human.age. In this example, we have both a struct by itself and then an array of humans here. So to access the value at a given index in an array, you specify the index like this, then you access that property. So find vote, create an external view function has voted, which takes an address and returns a boolean indicating if the address has cast a vote or not. So we need another function now. Below this has voted. It takes an address. Let's say voter, and returns a choices value. So it's going to be external view returns bool, indicating, okay, let's do the has voted function first. So we need to loop through the votes array here to see if this address has voted. And we can do that by just seeing whether or not they're in this array. So we can go for uint I equals 0, I is less than votes dot length, and we increment I each time. If votes I, then we access the voter address dot voter is equal to voter. Voter is the parameter here, but we're accessing the voter property and the struct in this loop to check whether or not they've voted. And then we say return true. Otherwise, we return false. Once this loop is finished, if they're not in there, it'll return false. And then create an external view function find choice, which takes an address and returns a choices value, indicating the choice on the vote cast by the address. For the find choice function, we can just copy this logic here we did just now. And instead of returning a bool, we're going to return a choice because we want to see what choice they've made. So you just do choice. Remember, this is an enum up here. And because it's an enum, you do not need to define any data location. So you don't need to say memory or anything like that. It's just choice. And the name is find choice. Inside of this address parameter, we can keep that as voter. And we want to see, first of all, if this person has voted. And instead of returning true, return votes I dot choice. And we don't need to return anything down here. Oh, this needs to be choices. Got a compiler error. In the compiler, you might see this message down here that says add an explicit return with value to all non-reverting code paths. Because the question does say don't worry about the case where there is no vote being cast, we will just leave this as is, but typically to remove the error, just simply return a choices.no as a default value, similar to how we did for false up here when the loop is finished, because that means that this address has not voted and therefore their choice would be a defaulted to no. Vote once. In this example, we only want to allow a given address to vote one time. So in this create vote function, we can call this has voted function we defined earlier and use it in a require statement to check if they've already voted. So here we just say require has voted. Now we're using the null check here to say we want them to not have voted. So we want a falsy, a false return value, not a true value. Passing the address, which is message.sender, the person calling the function. And if they have already voted, we say already voted. Now, if you notice in the compiler, it's got an error out because it can't access this function because it's an external function. To fix that, we change this to public. And now we can access this. Change vote. In this one, we need to allow someone who has voted to change their vote. So we're going to make a new function at the bottom, call it change vote, which will have a choice enum type here. This will be an external function. And inside of here, we have a require statement, which will say has voted. So we want this to be true this time. Want to make sure they've voted. Message.sender has voted. If they haven't, we say you have not voted yet. Now let's make a for loop to get the choice and then update it. Now we could actually use the logic up here in this function, find choice, since it does find the choice for us, but it doesn't allow us to update it in here yet. So let's just make a for loop for now, which does what we want it to do. So for u int I equals 0, I is less than votes dot length, and then we increment I each time. Inside of here, we check to see if votes dot voter is equal to message.sender. So we find the current address inside of the votes array, and then we access the votes. And then we say votes I dot choice equals choice, and then we'll update in the state variable within the votes array. We've got an error down here. I keep doing this, so it's choices, not choice. Okay, let's run this. Mappings are a crucial data type in Solidity. To be honest, most of them are crucial. All of them are crucial. But mappings are very, very popular because they're much cheaper than using an array. Now let's see what I mean by that. So with a mapping, we can take values of one data type and map them to values of another. So think of mappings as just objects in JavaScript or Java or Python. You'll have a key value pair, and you kind of just seen that in a previous section when I was showing the structs. You have a key that states what type the property is and the value you assign to it. In this example, we have a bunch of addresses and a balance tied to an address. So you could create an array of structs that contains, an account which has an address and a balance tied to it. But that's a lot of code right there. That's a lot to manage. A simpler way is just to have a mapping that has an address that points to its balance. So an address points to its balance. Address, unsigned integer. Remember, we use unsigned integers, not integers, because we don't want negative balances in Solidity. With a mapping, each address is mapped to a unique place in memory where it stores the uint balance. Looking up the balance is as simple as providing the address to the mapping. You just say balances and then you use these curly brackets and you pass through the data type, which in this case is an address. So let's begin. Add member. Mappings allow you to store and retrieve elements quickly with a key. Remember what I said earlier with key value pairs? The key points to a location in memory where the value is stored. The key can be any basic data type in Solidity. It cannot be a reference data type like a struct or an array. So there is a cheat sheet I'll throw up on screen now which shows you what you can pass through as a key value in the mapping and what you can't. So you can't pass a struct or an array as the key, but you can pass it as the value. So you could have an address, as you saw earlier, that points to an array of structs as the value, but you can't have an array of structs that points to an address. It doesn't really make sense when you think about it like that. Your goal is to create a public mapping called members, which maps an address to a bool. This boolean will indicate whether or not the address is currently a member. So in here, let's create a mapping address to a bool. It's public, and they will call it members. Create an external function called add member, which takes an address member and adds it as a member. So external. You can do this by storing true in the data location corresponding to the address. So now we get to see the syntax for updating a mapping state variable. So we say members, and then these square brackets, pass through the member address we just got here, equals true. So we're accessing the key value. So we're assigning the key as this member address that we get passed through, and we're assigning this value to true, which is a boolean. Great. Next stage, mapping retrieval. Compared to arrays, retrieving a value from a mapping is quite simple because you do not need to loop through the mapping. You cannot loop through a mapping in Solidity. It's simply just a key value which you cannot actually loop through, but arrays you can loop through, as we saw earlier. So how do we access a mapping value? Well, let's scroll down. Create an external view function called isMember, which takes an address and returns a boolean indicating whether or not the address is a member. So down here, isMember takes an address, member, external view returns bool, so whether it's true or false. We simply just do return members and then pass in member, and that's it. That's all we have to do. Compile. Oh, there we go. So we're simply just accessing the key, which we're passing as the address here of the member we want to check for, and that will return to us the value, which is a boolean. So is it true or false? Great. Next stage. Remove member. For arrays, removing elements can be an expensive operation, especially if you don't want to leave any gaps. So yeah, if you want to remove a specific part of an array, it can be very, very expensive, very tricky, because you have to loop through, know exactly where you want to remove that member. Again, which for a bigger array could mean many storage operations and is super expensive. But now there is a solution to this, something called a linked list, which we will not dive into in this tutorial, but it's basically just an amalgamation of different data types in Solidity to create a node which you can then refer to. Essentially, you can just stitch the previous node to the next node instead of having to shift elements around. But I can throw this on and I'll show you on screen now what that looks like, but don't worry about this. We're going to keep it simple in this guide. You literally just reassign the value. That's all you're doing. So there's no pop method or whatever method to do it. There are no methods on a mapping. It's just you access that key and you reassign the value. That's it. So create a new function, remove member. Again, it takes an address, external, and it's going to just, and all we're doing is just updating a value here. So we just say members, member equals false. So now they're no longer a member. Mapping to struct. Here's where mappings get interesting. We can map to many different types. So let's start with structs. So in this example, we have a collectible which has an owner, so someone who owns a collectible, whether or not it's for sale and the price of the collectible, and then you can map an ID to that collectible. Now this ID could be a unique product ID, ideally, which would map to that specific collectible. For example, you could have a Rolex, which has a specific serial number, which maps to who owns that Rolex, is it for sale, and how much is it? So your goal is to create a new token where every new user will receive 100 tokens. create a public mapping called users that will map an address to a user struct. Okay, so mapping, it will map an address to a user struct. It's public and it's called users. Then make an external function called create user. Create user. Create a new user and associate it to the message.sender in the users mapping. Okay, so remember how to create a new struct. So you want to say user memory new user equals user. The first parameter is the balance, so the balance should be set to 100, and the is active second parameter should be true, so true. And then now we can assign this new user to the mapping we just made. So we say users message.sender so we're setting the key to the current caller of this method call. The value would be the new user. So just to go over this one more time, we've defined a public mapping here, which maps a address to a user struct. We've created an in-memory struct called new user, and we've defined the first parameters as 100 for the balance and true for active. So this is an active user. And then we're assigning the key in the users mapping to this new user struct. One more thing I forgot. Ensure the create user function is called with an address that is not associated with an active user, otherwise revert the call. Okay, so we need to add in some checks here. So we say require users message.sender. We access the is active field and want it to be false. We don't want them to be active yet because we don't want to create another account for someone who's already active, right? Otherwise, we'll say already active. Great. So let's move on to the next stage. Map structs 2. Types of balances. Broadly speaking, a smart contract deals with two types of value transfers. Okay, this is where we start to think about something called okay. Okay. Broadly speaking, broadly speaking, smart contracts deal with two types of value transfers. The first one is the native currency Ether, which is stored and transferred using the native EVM mechanisms. So we've seen this earlier when we're doing we have a address and then we do a low level call to transfer the value to that address, and that value again is in Ether, the native currency of Ethereum. Or if it's on Polygon, it will be Matic. Whatever EVM chain it is, it will be the native currency of that chain. But there's another way we can represent currency. So a storage value, which can represent any kind of value on chain. And this is where the idea of cryptocurrencies come in. And the way it works is, well, you'll see in just a moment, but you're actually just modifying a state variable on chain. So you're changing the balance on chain. It's not like gas, where gas is required for the blockchain to do anything, right? Execute transactions. Now, in the smart contract you're building, you're maintaining your own balances in the user struct that has no relation to Ether. This means to transfer balances from one user to another, you just update the struct value. Again, so we're not transferring Ether now, we're just updating an on-chain storage value. Your goal, create an external function called transfer, which takes two parameters. So let's do this. Transfer. The first one is an address, call it recipient. The second one is a uint for the amount. In this function, transfer the amount specified from the balance of the message.sender to the balance of the recipient address. Okay, so let's do the first part first. We would do some standard maths to deduct the balance from the user and then increase the balance of the recipient. So we say users, and then we access message.sender key. And we can do the minus equals syntax, so minus equals amount. And then we increase the recipient, so we say users, recipient, oops, plus equals amount. So we deduct the balance from the user and increase the balance of the recipient. And then And now it says to add some security rules to this. Ensure that both addresses used in the transfer have active users. So we need to check the is active field. Ensure that the message.sender has enough in their balance to make sure the transfer can go without going into negative. Okay, so we need to have 3 checks here. If either of these conditions aren't satisfied, revert the call. Right, so the first one is we need to make sure these accounts are active or these users are active. So require, we'll just copy this here. It's true. And we say, oops, not active. Do the same thing below. And we just say recipient. And then we need to do another check to say, make sure that the message.sender's balance does not go into a negative balance. So we say require users message.sender dot balance is greater than or equal to the amount, or as we say, not enough balance. Okay, let's try this. Oh, there's an error down here. Oh, I didn't say the dot balance. Okay. Okay, let's try this now. Great. So if you're confused with this, all we're doing is updating a state variable. That's it. We're not messing with ether. And this is exactly how all ERC20s work on the blockchain. Nested mappings are huge in Solidity. They give you much more specific context as to what's happening for a given contract. So in here, it's giving an example of vote to address choice. So we want to see, first of all, what vote are you talking about here? So it will have a vote ID, let's say, and then we can pass to an address to see whether they voted yes or no for that given vote. Okay, so your goal is to make a public mapping called connections. Right, let's do this. So mapping, which will map an address to a mapping of an address to a connection type's enum value. Okay, so let's just break this down. Public mapping called connections, that's a name. The first thing is we need an address. So we need an address to a mapping of an address to a mapping of another address to the connection types enum, which is right above connection. This needs to be public and it's called connections. In the connect with function, create a connection from the message.sender to the other address. So in here, let's create a connection. So we'll have connections from message.sender to the other address is equal to connection type. And let's run the test. Great, so I just want to break this down a little bit more. Let's look at the test file here, and you can see how they're actually doing this. So in this test file, we have 2 addresses, A1 and A2, and we're testing to see whether or not this address is connected to another one. So when you see the prank keyword, it's just saying call this smart contract method with this address. So we're calling it with A1 here, and we're connecting A1 with A2, and we're saying that A2 is A1's friend. So it's like A1 is saying that this other address over here is my friend. What else? So we have unacquainted, friend, and family. So you could say that this person over here is either unacquainted with me, I don't know them, they're my friend, or they're my relative, they're my family. So that's a good, simple way of thinking how nested mappings are connected. Voting contract. So in this tutorial, we're going to build a voting contract and use the previous lessons that we've learned to apply it to a real world scenario. And this is concept of proposals. Now, if you've heard of a DAO or a decentralized autonomous organization, they often use the term proposals to create, well, what it is, a proposal or an idea to the DAO or the organization in as to how and which direction it should go in. So we're going to focus on creating a contract, a voting contract that allows members to create new proposals. This contract can contain many proposals which will be voted on by a group of members. Each proposal will keep track of its votes to decide when it's time to execute. At execution time, these proposals will send Calldata to a smart contract, and the Calldata could be anything. We could have a voting system that allows 100 members to decide when to upgrade a protocol. The Calldata might target a function with the signature upgrade and send over the new protocol implementation. In short, it's a contract that allows users to vote on a proposal or an idea, and when that proposal or idea reaches a certain limit of votes, it is then executed, and that execution can be any sort of custom logic that you want. Proposal storage. In this stage, we're going to focus on the storage of new proposals. A proposal should take in some Calldata and a target. We've seen that in a previous section. If you're not sure, I'll include a link to it on screen now. When the proposal passes a voting stage, the contract will send that Calldata to the target. To begin with, the yes and no count should be 0 until we record some votes. So the goal is to first create a public array. So we'll say uint, proposal, square brackets, and should be public, should be proposal. So this is an array of structs here that contains all the proposals. Then we'll have a function called new proposal, which takes two arguments, an address, we'll call it target, and some Calldata of type bytes. So Calldata bytes. Oops, I mean data. Remember, because this is external, we can actually use Calldata as a data location of the incoming data here. So it's read only and therefore cost very little gas or no gas at all. And then here, create a new proposal with the arguments passed in and the yes no vote count initialized to 0. And then we need to add it to the array. So similar to before, we just say proposal memory. We'll call it proposal. We could call it new proposal, but that's the name of the function as well, so that would cause a clash. Equals proposal, and then there's four properties in here. So we have target, data, yes count, and no count. The target and data are the parameters passed into the function, so target and data, and the other ones, yes and no count, are initialized to 0. And then we push this into the proposals storage array. So proposals dot push proposal. Great, so let's move on to the next stage. Oh. Cast a vote. Now that we have proposals with vote counts, it's time to create functionality for voting. Now our goal is to create another function called cast vote. So function cast vote. It's going to take a uint called proposal ID and a boolean to say whether it's true or false, indicating if they support the proposal or they don't support it. So we'll call this is supported. Oops, this will be external. We can make a storage pointer here. So we can say proposal storage selected proposal is equal to proposals and then proposal ID. So now we're selecting the, so we're just selecting the index, the value. So here we're just selecting the proposal at a given index. So the ID is assumed to be the proposal's ID. And then we have an if statement to say if is supported. So if it's true, we say selected proposal dot yes count plus plus. So we can increment it like this. Else, we're going to say selected proposal dot no count minus minus. And we've got a compilation error. Oh, no, we don't. Let's check the tests. Oh, my mistake. So we don't want to decrement the no count. We want to increment the no count. So plus equals 1 again. Or just plus plus, but we'll keep it simple. We're just plus plus here and plus plus there. Let's run the test again. Perfect. Next stage. Multiple votes. Now this challenge here is probably the hardest one in the entire course. So we're going to break this down step by step. And the reason why is because it leaves implementation up to you. And there's a lot of different ways we can go about doing this challenge. And it's actually my favorite one, to be honest, because it's so um, custom. It's a very customized experience here. Now, we need to handle the case where an address votes twice. We could prevent voters from voting twice, but what if I've already voted and I've changed my mind and I vote a different answer? So we can allow them to change their votes, and this means that if the address previously said yes to a proposal and then switched to no, we want to decrement the overall no count for that proposal, sorry, the yes count, and then increment the no count and vice versa if the other way is true. Now the goal is to modify this cast vote function to allow voters to change their vote on a specific proposal. The implementation is completely up to you, and you'll need to figure out a new way to track which addresses have already voted. The tricky part about this challenge is we have to know what specific proposal a given address has voted for, and then what did they say about that address. So it kind of looks like a nested mapping could be used here, and that's what we're going to use as part of the solution. The first thing I want to do is to find what variables we're going to need. So we've already said we need to know what address has voted on which proposal. So let's make a mapping here. Let's have a uint, or an address. So a user, a voter, is going to map to an array of proposal IDs, because that's the only way we can access each given proposal, as we did here. So we're going to say uint array of uint, and this would be public, and we'll call it user proposals. This is all the proposals a user has voted on. So we know that if they haven't, so from this mapping, we know every single proposal a given address has voted on. Now, how do we know what they said about that given proposal? We could have another mapping below this, which would have an address, so that same user, to that specific proposal by its ID. So we say uint, mapping uint, and then in this mapping we're going to point to the actual proposal itself. Sorry, whether it's a yes or a no. So we're going to use a boolean here, and this will be called, and we'll just call this user votes. Now, just to go over this one more time, the first mapping is just to say what proposals has this address voted on, and the second one is more detailed to find the relationship between, okay, this user has, so for this given proposal by its ID, this user has said yes or no, and so now we know what they've said for a specific proposal. So I've just renamed this to user proposals IDs because it actually just stores the IDs of the proposal, not the proposal itself. And this one can stay as user votes because the yes or no is enough information to know what they've voted on for that given proposal. So in here, what I'm going to do is create a uint. We'll call this current user proposal IDs, and this is going to be accessed using the user proposals IDs mapping, passing the message.sender, and now we have an array that contains all the proposals they've interacted with. So first, want to see, is this array even bigger than 0? So let's say if current user proposal IDs dot length, which is a innate function on arrays, equals 0, so they haven't done anything at all. We're going to assume that this means that this is their first time voting. So we can kind of just copy this logic here, put it inside. How do I reformat in here? This ID, I'm not too sure. I'm just gonna reformat it like this. So let's just ignore this code for now. We can comment this out so it doesn't execute. We need to increment the yes count and decrement the no count. That's fine. But we also need to update. Sorry. We also need to update this user votes mapping now that exists. So this is correct because we're updating the state of this proposal here from its ID. And we need to say user votes message.sender proposal ID equals true. So they've said yes to this proposal, and the other one we're going to say false. So now, this is the first time they've voted on a proposal, and it would also presumably have to be the 0th index. So it's going to be the first proposal in this example. But fortunately, that's how these tests are doing it. So they're only passing in one proposal, which is at the 0th index. So we don't need to worry about anything else here. If the length is not 0, that means I have voted on something. So we can say else. Let's create a boolean here to say current votes will be equal to user votes. So we're accessing that same mapping again. And then we'll get the proposal ID in here. That returns to us true or false. And then we're going to say if current vote is equal to false and they are supporting this vote. So it was false before, but now they are saying, in fact, I do support this proposal. We then need to do a couple things. We need to increment the yes count on the state variable, but also decrement the no count. And then we need to update this mapping again. So user votes message.sender passing the proposal ID is equal to true. So they said yes. And the other scenario is else, or just, yeah, else if current vote and is supported and is not supported is equal to false. So we're saying if they voted yes before, but now they've changed their mind, we'll just take the same logic here and just invert it. Great, so we got a compiler error down here. Did you mean, okay, yeah, line 23, current user proposal IDs. Okay, I kept putting an S there. And this, oh, This array of uint here needs to be memory because we need to push in this value into the user proposal IDs if it's their first time making a vote. So in here, we also need to say do user proposals IDs access the key, so it's message.sender. We have the array now, and we need to do dot push proposal ID, and the same for this one. So we now know which proposal they voted on for the first time voting in this mapping here. Perfect. So we can delete this code now. Let's move on to the next stage. Voting events. Events are crucial in Solidity because they inform the front end and back end server of any event that's taken place on the blockchain. Without events, we would have no idea what's happening on the blockchain. So let's add some new events we can listen to closely. We define events as event proposal created. Pass in the type, the uint, and then the name of the argument. So we'll say proposal ID. This can be anything you want. And the next event is a vote cast. So vote cast, pass in two arguments, a uint or proposal ID. So which proposal are you voting for? And then an address to say who voted on that address. I mean, the proposal. And now we need to add these into the functions, which is very easy. So for the first one, proposal created, we just add it at the bottom of here. You say emit proposal created, and then pass in the proposal ID. Now, if you put this at the end of this logic here, it will be the length of the proposal array minus 1, because remember, the ID is tied to the index in the array. So we want to say proposals.length minus 1. And for the next one, inside cast vote, at the bottom, you can just say emit vote cast, and we pass in the proposal ID and message.sender. So I wanted to show you, let's go back real quick. I want to show you the test here. So in Foundry, we can watch for events as well. So Foundry is such an amazing tool. And if you haven't used it before, I highly suggest you check out my previous video on how to use Foundry and how to use the best practices so you get the most out of it. In here, you can listen for events by getting the logs. So it's actually doing record logs, new proposal. So it's calling the proposal method, and it's checking to see what's in those logs because the events are stored in the logs. The entries in the log is just an array here, and you're checking the length, similar to what we're doing in this function here, to see if there is anything in this array that means that there's an event being emitted. And then we can check the function signature, which is the signature of the event we've just defined called proposal created that accepts a uint256. So we're using the same syntax we used in the previous section to get the function signature, and then we're hashing it. In the next assertion, we're checking to see if the data in the event is equal to 0, so we can decode that using the abi.decode method. Voting members. It's important for us to maintain a list of voting members. After all, it's easy for anyone to make hundreds of Ethereum addresses very quickly and vote with each of these addresses, and the only thing stopping them is just gas and effort, which is true, right? But fortunately, because of gas, it prevents a lot of these spam attacks, or all of them really. When a single person operates many accounts, it is known as a Cybele attack. Any system that is set up to handle this is known to be Cybele resistance. So the goal, create a public constructor which takes an array of addresses. These addresses, plus the deployer, should all be allowed to create new proposals and vote on these proposals. If anyone else attempts to create a proposal or cast a vote, then the transaction gets reverted. So we basically need a whitelist here. And the way I'm going to do it is beneath these variable definitions, I'm going to create a constructor, and it takes an array of addresses. We'll call it, we'll call them whitelist, and we're going to make a state variable in here. Let's call it address, and it will call whitelist, not public because we don't need the getter function. And we also need a deployer, so address deployer, so who deployed this. Now inside this function, inside of a constructor, you can actually do a for loop. So that's the only way we can assign the values in this array here to the state variable. So we just do for uint I equals 0, I is less than underscore whitelist dot length, so the parameter being passed in, and then we increment I each time, and then all we do is we say whitelist dot push underscore whitelist square brackets I dot just I, and that's it. So it's going to push in, or let me just charge my Mac. So we just push in each address in this constructor to the state variable whitelist, and now we have assigned the deployer to message.sender. So we've done that. That's part one. We still need to, let's check the compiler error. This needs to be memory. We need to create a modifier essentially to check is a person calling the addresses either in the whitelist or the deployer. So at the bottom, I'm going to make a modifier. So we called only whitelist. Obviously, the cheapest option is to first just check whether or not they are the deployer. So the cheapest option is to just say if message.sender equals deployer, then we just say we're going to exit out. And actually, I'm going to define a boolean at the top here to say is allowed equals false. And you'll see why I've done that in just a moment. Beneath this, we're going to have a for loop to say uint I equals 0. We loop through the whitelist dot length, and we increment I each time. If whitelist I is equal to message.sender, we then say is allowed equals true, require is allowed, else not allowed. So yeah, so this require just reverts the transaction if they're not on the whitelist or the deployer. Let's run this. Why did it error? So I got an error in the test. Call did not revert as expected. So let's look at the test. Test vote non-member. Okay, so anyone. I forgot to add it to the actual functions. So we need to say only whitelist here after the parameter definition, and then only whitelist again. Now we can call it perfect. Execute. Execute vote. In smart contract governance systems, there is usually some minimum voting participation that must be reached before a proposal can be executed. Most governance systems today use coin voting, which is why I mentioned earlier with DAOs, as they typically use an ERC20 token that decides your voting weight. Once 10 members have voted yes on a proposal, we can then execute that proposal. So let's update the cast vote function here to execute the proposal when the 10 yes votes have been registered. So at the bottom, so we already have the select proposal that we want defined here at the top. So we can check to see if this proposal .es count is equal to 10. We're then going to call the target, which is on the proposal struct here, with some data. So we're going to execute a function on that target address. So we just say bool success equals selected proposal dot target dot call, and then we don't need to use the curly braces, just the parentheses to say um, selected proposal dot data, and we require this to be successful. Great, so now we are done with the voting contract. Contract inheritance. As with many object-oriented languages, Solidity includes inheritance as a feature. Now, inheritance is huge in Solidity, and you'll see it used almost everywhere. So, for example, if you want to make your own cryptocurrency token, you will most likely, no, you will have to inherit from the ERC20 smart contract, specifically the IERC20 interface. So we're going to dive into how we can do these sort of inheritance models in this section here. Inheritance means that you can create an object with some values or methods and use it as a base for other objects. In Solidity, the objects we are referring to are contracts and interfaces. So if you make your own token, you inherit from the IERC20 interface so that your contract can be interpreted as an ERC20 token. This use case may seem quite similar to libraries. So we do have libraries in Solidity as well, such as Math library, other libraries like Counter as well. And that basically just saves you from re-implementing the same logic into your smart contract. So it's just cleaner and more gas efficient to do it that way. We'll take a look at why it's powerful, and of course that comes with trade-offs. With the time and practice, you'll be able to understand those trade-offs and figure out which tool is right for that particular job at hand. So let's begin. Inherit. Traditionally, inheritance is when one class copies or inherits another. Now, throughout this lesson, you'll see the terms base and derived. So the derived class inherits from the base class. So in this example, the base class is the hero, and the derived classes are the new ones we're going to create from the hero. Our goal in this task is to create two contracts, Mage and Warrior, which both inherit from the hero contract. So we'll just make contracts Mage is hero, and the same for Warrior. Contract Warrior is hero. Simple. Constructor inheritance. In the previous example, the base contract, the hero contract, had a state variable with an initial value. So let's have a look. We have a state variable here on hero called health, and on deployment, this gets set by the constructor. Correct. Now, can we pass that initial value into the base constructor when we're inheriting it? Yes, we can. So the syntax looks like this. So let's head back over to our derived contracts. And all you do is pass in a parameter into hero here. So let's modify our superhero so that warrior has an initial health of 200, whereas the mage has 50. So in here, we just say 50. And for warrior, we just say 100. Oh, we've done something wrong here. So, 200. Great. Next stage, virtual override. It's time to introduce two new function keywords, virtual and override. Now, sometimes we want to leave a function on a base contract open to re-implementation from its derived contract. So what this means is, here in Hero, we'll have a virtual function here, and as you can see, it has no implementation. How can that be? How can you have a function that has no implementation? Well, that's because this contract is defined as an abstract contract. Abstract contracts are similar to interfaces in that they define what functions exist on a given contract. However, on an interface, none of those definitions can have any implementation logic. It's just a function signature. Whereas for an abstract contract, some of them can have definitions, like this one, take damage, but then other ones marked as virtual can just be the definition function signature itself, and that means that the derived contracts here can define their own implementations for this given attack method here. So let's head back to the task, scroll down. You'll notice the hero.sol has changed again. The hero contract is an abstract contract. Yep, we've just seen that. And the attack function is now virtual, so we can override it in the derived contracts. An enum called attack types, yep, has been added to hero. And there's a contract called enemy.sol, which has a method called takeAttack. So your job is to implement the attack function on the warrior and mage contracts. First, add an override function called attack to both the warrior and mage contracts. This function should take an enemy parameter. Okay, let's start with mage first. So function uh, function attack. It's gonna take an enemy parameter, and it's going to be external. It's gonna override the inherited. So this will override the attack function on here as it's marked virtual. Actually, we can keep that as public because that's what it is on the virtual one. And then in here, for the mage, invoke the enemy's take attack with the spell attack type. Okay. So inside of the mage attack function, we have to invoke the enemy's take attack. So we're calling the method on enemy.sol in here. And we already have this interface type defined in here. So we have enemy dot take attack. So we know that this method exists on here because we have the enemy type here. So we can just call enemy.take attack, and then we pass through the attack types. So we say hero dot attack types dot spell, and then we copy this, put it into hero, and just change this to brawl. So let's run that. Great. So we are virtually unstoppable. Next stage, super. Super cool. In the last stage, we wrote an override function for an unimplemented function on the base contract. In other cases, the base contract will have functionality in its virtual. So it doesn't have to be like this. So basically what that means is now the hero contract is not an abstract function. So it still has the virtual function, but as you can see, it does have its own implementation. So how do we actually call this function here from the derived contract? Well, this is where super comes in. So super allows us to access the parent's properties and functions. Let's scroll down to the goal. Your goal, add the super. The attack function is now implemented by the hero base contract. It will take the enemy as an argument and decrement energy from our hero after each attack. Let's invoke this base contract function from within the attack function for both derived hero contracts. Okay, so similar to before. So within this attack function, we just have to call the super dot attack. We pass in enemy. And we copy this, put it into the other one. So what we're doing here is we are calling, actually let me just format this better. So we have our own attack function here, which is overriding the virtual method on the parent, but we can still call the original implementation here by calling super.attack. Let's run the test. Next stage, ownable. Base utility ownable. It is often quite useful for a base contract to have utility functions and modifiers. So in this example, we have a depositable contract that requires a deposit of at least 1 ether. So we saw this in the first examples actually, and so we saw this in the escrow contract in the second part. So here it requires a deposit of at least 1 ether, and this requirement comes from the base contract in this example. So we have an escrow which inherits from a depositable, and that depositable contract has a modifier that requires at least 1 ether. And we can access that modifier by just calling it as normal in the derived contract. So our goal on the collectibles.sol here, you'll see the collectible contract inherits from the ownable contract. So this is inheriting from ownable, which comes from this one here. Your goal is to fill out the ownable base contract, which will be used by the collectible contract. The owner should be defined in the ownable base contract. Ensure that mark price can only be called by the owner. So we need to copy what they did here basically. So all we have to do first define who the owner is. So address owner, and let's make a state variable owner. And then in here we're going to say owner. Actually, sorry, we don't need this. Okay, let's start again. All we have to do is make a constructor, and we need to assign a state variable, which we'll call owner, to the message.sender, so the person calling this. Next, we create a modifier like we have here. So I can just copy this, paste this here, and change this to only owner, and require that message.sender is equal to owner. Otherwise, we say only owner. Perfect. And then finally, we have to ensure that mark price can only be called by the owner. So in collectible.sol, we have to add a, oh, it's already there, only owner. Perfect. Right, next stage, multiple inheritance. So it's possible to inherit from multiple contracts. The derived contracts will inherit state variables and functions from each base contract. So you may see this, especially with something like an NFT. So if you make a NFT contract, it would most likely inherit from ERC 721, maybe ERC 721 URI storage, and then only owner and a bunch of other standards that you want to implement into your custom NFT contract. In this task, the collectible contract now also inherits from transferable, a contract which has not yet been created. So in here, we need to make that. Your goal is to create a new contract transferable that will allow the collectible to transfer its ownership to another address. In the transferable contract, create a function called transfer which takes an address for the new owner. Have this function pass transfer ownership from the current owner to the new owner passed in. And only the current owner can call this. Okay, so this is kind of hinting at ELC20s and even ELC721's transfer method. Inheritance order. So when inheriting from contracts, the most base contract should be furthest left in the comma separated list. So this matters because there is an issue down here that says, in this example, we have the base contract, which is the parent, and a derived contract called middle is inheriting from the parent, standard. The most base contract starts first, and then the next inherited one, and then the next one, and so on and so forth. If you fail to do this correctly, you'll see an error called linearization of inheritance graph impossible, which is pretty scary, but it's pretty easy to fix once you know what it means. In this task, we are doing multiple inheritance, so we need to make a new contract that inherits from ownable so that only the owner can transfer to a new owner. So this contract is going to be called transferable is ownable, and then in here we have a function called transfer, which takes in a new owner, and only the owner can call this. So we say only owner external. All we're doing is updating this state variable here to the new address. So owner is equal to new owner. Therefore, the collectible contract depends upon the ownable one first and then transferable. Otherwise, you'll get this nasty error down here, linearization of inheritance graph, impossible. Let's run the tests. Congratulations, you've now finished the course. You are a qualified Solidity developer, or at least you can believe that you are, because if you understood everything from start to finish, and I mean really understood it, then you have the fundamentals to go on and prosper within Web3, whether that's building your own project, joining a project, or maybe you want to um, implement Web3 into your existing business in some way, shape, or form. Now you know how the blockchain works and how to create your own smart contracts. Whether you need help on the course or on what to do next, just ask in the comments below and I will get back to you as soon as I can. If you don't feel as confident yet, there is another course you can do which is a little bit more advanced. But honestly, once you have the fundamentals down, all it is from there is just experience and go get yourself a role as fast as you can. If you want to gain more confidence, then I encourage you to join hackathons. That's how I built up my confidence and skills. It teaches you how to work in a team under pressure, and you get to learn so much in a short time span. I can always vouch for hackathons, and you should too. The best places to look for a new job I will link in the description below, but I'll let you in on a little secret that I know. If you really, really want a job and you want it now, I really suggest that you head to as many events as you can. So I mean real life events. Go to Web3 tech events, Web2 events, and just meet as many people as you can. Be yourself, and you'll be surprised at how many opportunities exist behind the scenes and are rarely advertised on job boards. The harsh reality is, it's not what you know or even who you know, it's who knows you and your mission. And if your mission is to dominate 2024 by being the best Solidity developer that you can be, then somebody needs you on their team as soon as possible, and they're willing to pay a high ticket. Again, a big congratulations, and I look forward to your future success in 2024.